Okay, hi students. So today we will cover the external flow across cylinders and sphere. So we know it's very common to see a flow over cylinder and sphere. So normally it is highly for cylinder is highly applicable for shell and tube heat exchanger. Is involve both internal flow and external flow for heat exchanger. And for sphere, we can see in many sports such as soccer, tennis, and golf. Okay, is involve the flow over a spherical ball. So unlike Reynolds number for flat surface, in cylinder and sphere we use external diameter to replace the L. So Reynolds number for cylinder and sphere is equal to rho times velocity times D, your diameter, divided by dynamic viscosity, or velocity times external diameter divided by kinematic viscosity. And the critical Reynolds number for cylinder and sphere is 2 times 10 power of 5. Okay. So next, this is the formula. It don't have different formula for laminar and turbulent flow because in this formula, it already cover both. But you have to take note that the fluid properties are evaluated at firm temperature for cylinder, while for sphere, the fluid properties are evaluated at T infinity, except for dynamic viscosity, where it is evaluated at the surface temperature. Okay, so these are the formulas for cylinder and sphere. Okay, we have a more compact correlation across cylinders because cylinders is applicable for tube and pipe, and they are not always, the tube and pipe are not always in cylinder shape. Okay, it could be in sphere, in square, tilt, hexagon shape, and many other shape. Okay, so this is the correlation for other shapes. Okay, where NU equal to CRE power of M PRN, where your N is always 1/1/3, and your C and M is given in this table 7.1. So you have to find the correct shape and find the correct shape and the respective formula that's suitable with your shape. Okay. So now let's look at example 7.5 and 7.6. So in example 7.5, a long 10 cm diameter steam pipe whose external surface temperature is 110 degrees Celsius passes through some open area that is not protected against the wind. So determine the rate of heat loss from the pipe per unit of its length when the air is at 1 atm pressure and 100 degrees Celsius and the wind blowing across the pipe is at velocity of 8 meter per second. So first step is you have to find the T film temperature to know the properties. So your T film temperature is 110 degrees Celsius plus 10 degrees Celsius divided by 2. So it's 60 degrees Celsius. So once you know this film temperature, you can look for the properties value in appendix. Okay, so this is air. So we look at table A.15, properties of air at 1 atm pressure. So we are looking for at 60 degrees Celsius. So these are the details. So you can get your Prandtl number, kinematic, K, and your density. Okay, so from table A5 in appendix, your K is K is 0.08. Your PR is 0.2707. Your kinematic viscosity is 1.896 times 10 negative 5 meter cube per second. Okay, so once after you know the properties, you can calculate for the Reynolds number. So RE is equals to UT velocity is 8 meter per second, diameter is 0.1 meter, so divide by 1.896 times 10 negative 5. So you will get the Reynolds number of 4.219 times 10 power of 4. Okay, scroll down. Okay, next. So step 2, you have to find the Nusselt number based on the formula. So for cylinder, formula is quite long, so make sure you key in the correct numbers in your calculator. 62 RE 1/2 PR 1/3 and multiply by 1 plus RE over 200. Okay, 5 over 8 over 5. It's very lengthy, so let me check if I made any mistake here. Okay, I think it's correct. Scroll down again. Oops. So you have to plug in all the values. Everything is known. So you already have your RE, find from the table. Okay. So once you calculate this, you will get Nusselt number as 124. Then step 3. So we have to relate the Nusselt number with the H, heat transfer coefficient, HD over K. So your H is equal to K and U over diameter. So your K is 0.02802. Okay. Multiply by your Nusselt number 124. Divide everything by 0.1 meter. Okay. So now your H is 34.8 W per meter square. Okay. So now we have to we can solve for Q, heat transfer, rate of heat transfer. So Q equals to HA T surface minus T infinity. So we need to find out the area of the cylinder. A is equals to pi dl, because here is mentioned per unit length, so your L is 1 meter, pi times 0.1 meter times 1 meter. So your area is 0.314 meter. Okay, so now you can solve for your Q. So H 34.8 K multiplied by your area 0.314. Your surface temperature 110 degrees Celsius, 10 degrees Celsius. Okay, you don't have to convert this Celsius to Kelvin because it is a delta change. So we can start with K. K M. So your final answer Q is 1093 watt. Okay, let's look at our timing.